Hi folks. So last time we were talking about sequential logic and making finite state machines. We did some examples. We did them in terms of circuits, but mostly we did them in terms of code. So we drew our state transition diagrams, we wrote out our state transition tables, and we wrote some code that enabled us to implement these finite state machines. So we're going to move on from that, and we're going to start talking about interfacing systems. And so this is the first of several different interfacing system subsections. We're going to talk about A to D and D to A today. So why do we care about analog and digital numbers? Well, the physical world, the world that our systems are interacting with, is mostly analog. But we know, of course, that our mechatronic systems are going to be implemented using some sort of microcontroller, which is going to be digital. And so we need to be able to have some sort of connection between our digital controller and our analog world. And in order to do that, we're going to be able to convert values back and forth. And mostly we're going to deal with voltages. So voltages in the real world are going to be converted to numbers in the digital world, and then numbers in the digital world are going to be converted to voltages in the real world for the purpose of actuation. So we need to worry about numbers going back and forth. So we can represent numbers in a bunch of different ways. We're very familiar with our decimal representation. So our decimal representation is base 10. That's the one that most of us have learned from the time that we learned about what numbers even were. So we count from 0 up to 9. And when we get to 9, we roll over that next digit. We often call the tens digit. And we restart our ones digit at 0, and we count up again. And so we can do the same sort of thing in other bases. And I'm sure you've seen this, but you may not think about it too much. So for instance, we could do it in base 8. So we'll start with that ones digit, and we'll count all the way up, not to 9, but to 7. And then we'll roll over not our tens digit anymore, but our eights digit. And so you can see that when we get to a number that is 10, that is equivalent to our decimal 8. So if we're talking about these different numbers, you can see that 10 versus 10 looks a little different here. So let's go ahead and remind ourselves that if we're talking about decimal, we're going to put parentheses and a subscript 10, base 10. And if we're talking about octal, we'll do a subscript 8 to tell us it's base 8. Now, decimal is what we consider to be normal. It was developed by Roman, Chinese, and Arabic mathematicians. But octal was also developed by some cultures in terms of counting systems. Now, those cultures have not been the ones that have dominated mathematical publications, so maybe it's not as obvious, but there was a reason that those cultures developed octal. So the reading that I found suggested that they were still counting on their hands, but instead of counting their fingers, they were counting the spaces between their fingers. So if you look at your hands, you'll see 8 spaces between your fingers. Normally we'd do that as a question in class and make everybody puzzle about it for a while, but it's hard to do that as a video. So I'm sorry, there's the answer right away. So octal is great. We're not going to really use octal in this class. We're going to be more concerned with hexadecimal and binary. So binary is our base 2, and that's the one that you've seen before, where each of these is either a 0 or a 1. Each digit, is a 0 or 1. And so it's got this direct connection to our logic. Everything is on or off, true or false. Very easy to picture it as being a whole bunch of switches. We typically represent these in blocks of about 4 digits here. So I've got 4 digits, and then I've only got the first one on the next, but I'd have another block of 4 digits. And I'll often put a space in there just to make it easier to read, because when you think about binary, one of the things you think about is the fact that to represent a number, you're going to have a lot of digits. So for instance, 16 in decimal is going to require 5 digits in binary. So binary is not a very compact representation, but it does have a good connection to logic. So thinking about that, that's why we often are going to use hexadecimal instead. So hexadecimal, you can see, has the same sort of breakpoints. So when we get all the way up here to flipping over this 5th digit, so we've got a bunch of zeros again and a 1, you can see that we've flipped over the 2nd digit of hexadecimal. No coincidence there. The base 16 is a good compact representation of binary. And so you'll see hexadecimal used a lot when we want to talk about binary numbers, but we don't want to use all the digits. There's this nice one-to-one mapping here. Also notice that in order to have enough digits, or enough, digits isn't the right word, I had to have enough symbols. There we go. So we only have in our decimal history here, we've only got up through 9, so we had to add some additional symbols to represent numbers in a single digit. So A is 10 in a single digit, B is 11 in a single digit. So if we want to talk about a single digit here, which you may have seen this before, it's got a special name. We'll come back to that in a second. If we want to talk about 2 digits, we would call that a byte. But if we want to talk about a single digit, we might call it a nibble, which is humorous. That's a joke invented by people that do this sort of thing. Not me, obviously. So when we think about computer systems and we think about our implementation of mechatronic systems, we need to be able to get this information, as I said, from the analog world, the physical world, into the digital world. So we need to have this conversion back and forth. And so I'm going to show a lot of this conversion with a number line. And you've probably seen a number line before. So you can see that on my number line here, I've got analog numbers, 0 through 7. And obviously with analog, we can have infinite variations between these numbers. Okay, so we're talking about real numbers. We're talking about all sorts of spacing in here. But in the digital world, we're talking about only numbers that can be represented in binary. And so each of these has essentially a point on the number line, not a spread on the number line. So when we think about the number 1.6, well, it doesn't map exactly as I've shown the number line here. You could certainly change it up a little bit, but it doesn't map exactly to a number, and so we're going to need to round, essentially. And so we're going to have these buckets of analog numbers that are going to all converge into a single digital number. And so that's the conversion that we're looking at. This is quantization. So there are different coding styles. The one that we're going to see a lot is what we call natural binary counting. I'll show you some other examples. So when we think about number representations then, we've got our analog numbers, things like pi, and we've got our digital numbers, which is all ones and zeros. So if we think about advantages and disadvantages of each of them, digital we know is going to be easy to manipulate using a computer. That's why we do it, because we need our computer to work. And it's also going to be less susceptible to noise. We talked a little bit about noise margin previously. Well, noise margin is a good reason for digital because you can have a little bit of immunity to noise there. But unfortunately, as I was just showing you with that number line, we have finite precision with our digital numbers. We can't represent things like pi exactly. We do lose information when we sample. So we are rounding off 1.6 into the same number as 2. And so we don't, when we get to the digital side, we don't know which one it was. We have lost information. And then there's always a little bit of time lag. So when we actually do the conversion, there's a little bit of a time lag there. Maybe it's not huge relative to our slow mechanical systems, but it's still there. And then obviously the disadvantages of digital are going to be the advantages of analog and so forth. So analog is going to have infinite resolution, instantaneous. It's going to have disadvantages of noise and repeatability, and it doesn't work so well with computer. Okay, so there we go. So how do we represent this for people to read? Well, as I said, we're going to subscript these things to make sure that we know which one we're dealing with. So even though we often are thinking in terms of binary, we will represent in terms of hexadecimal. It's just the most compact. In terms of your Arduino code, you can use things like this leading B or this leading 0x in order to identify for the user which type of representation you're using. And then if you're using decimal, oh, I lost my tab in there, oops. If you're using decimal, there's no formatting needed. So let's think about binary then. We're going to understand that hexadecimal and octal are convertible easily, but let's talk about binary. So binary is going to have a bunch of bits, and so each of these bits is going to be represented in this thing by a D number, and so there is a one on the far right that we're going to call the least significant bit, and one on the far left that we're going to call the most significant bit. And so each one of these is going to represent something multiplied by a power of 2, because it's base 2, it's binary. And so you might have a number that looks something like this. Again, I'm going to subscript a 2 to remind ourselves that we're talking about binary. And again, the left is the most significant bit, the one that's multiplied by the highest power of 2. and the right is the least significant bit, the one that's represented by the lowest power of 2, which is 2 to the 0. So in this arrangement, left being most significant bit and right being least significant bit, it's called big endian. Sometimes you'll see it reversed. There's nothing that says it absolutely has to be one way or the other. This is just a convention that we have accepted. And so if we reverse it, it would be called little endian. If you want to know the history of that, it comes from Gulliver's Travels. And again, someone finds it humorous. So if we wanted to convert this from binary to decimal, as an example, let's take this number from the previous one. So let's just start from the least significant bit. So I've got 1 times 2 to the 0. I've got 1 times 2 to the 1. I've got 0 times 2 to the 2. I've got 1 times 2 to the 3. And then we're going to jump over the gap there. And we'll 0 times 2 to the 4, and 1 times 2 to the 5, and 1 times 2 to the 6, and 0 times 2 to the 7. But I know what 2 to the 0 and 2 to the 1 and so forth are, so I can work those out. And if I add those all up, I'm going to get 107 in base 10 decimal. So this is an example of what we call straight binary counting. Everything is unsigned. There's no sign convention. Everything is assumed to be positive. So same sort of thing represented here for counting up to 7. So here's a couple examples. Again, if we were doing this in class as normal, we would work through these as a class. We would have somebody write them on the board. But let's go ahead and assume that you are going to pause the video at this point and work these out for yourself to make sure that you are comfortable converting back and forth. So I'll sit here and wait. But not very long, because you can pause it and you can come back to this. So another scheme that you'll see that's related but not the same is BCD, binary coded displays. So this is when you've got a 7-segment display, as we will do in class. And so your 7-segment display has 7 segments. And each of those 7-segment displays has to represent a decimal number. So if we want to represent 0, we're going to illuminate segments 0, 1, 2, 3, 4, and 5, but not segment 6, which is why we're showing these little stars here to identify which segments have been illuminated. If we want to represent a 1, we would illuminate only segments 4 and 5. If we wanted a 2, we'd do 0, 5, 6, 2, and 3, and so forth. So if we want to represent a number on a 7-segment display, what we might say is that we want to represent the number 364. But to represent 364, we don't want to represent it as binary. We want to represent each digit individually, because each of those digits is going to be on its own separate display. And so we might then convert each of these. So the 3 gets its own block of 4 bits there. The 6 gets its own block of 4 bits there. And the 4 gets its own block of 4 bits there. And so it looks like binary. It's using techniques associated with binary, but it's not exactly binary, so we will identify it as BCD. All right, so let's go back to binary numbers. Binary numbers, I mentioned so far that we had positive numbers. Well, sometimes you need negative numbers too. It is amazing, but when you want to do math, you sometimes need negative numbers. And so you have to have some way to represent a negative sign. Binary does not inherently have a negative sign, and so we have to have some sort of agreement among users of what a negative sign means. And so we have to have something that is a common method. So I've got 4 different methods here: unipolar, offset binary, sign extension, and 2's complement. These are 4 different ways to deal with a negative sign. And if you're reading through a data sheet, it might tell you for the particular device that you're using which method it's doing. Probably only going to be super relevant if you're looking at an analog to digital conversion chip. So in that case, it'll spit out a digital value, and you need to know which one it's using. So the first one is unipolar. And so unipolar just says there will be no negative numbers. I will never allow negative numbers. And so in that case, we're only going to have code values between 0 and 2 to the n minus 1, n being the number of bits. So in this case, for instance, I might have a voltage range between 0 and 5, kind of like your Arduino. And so that might get mapped to digital values between 0 and 111. And so because they're binary numbers and you and I know what we're talking about, we're going to remember that we could also write these out as decimal equivalent of the binary numbers, and I'll subscript those with 10 to remind myself that they are decimal equivalents. And so you can see that for each of these, there's this gap The gap between each of the numbers is all about 0.71, and that is what we might call our quantization interval. And so in this scheme, again, unipolar assumes there is never a negative number. Instead, if we know that there's going to be negative numbers, we might choose offset binary. So offset binary says I'm still going to use only positive digital values, 0, 0, 0 through 1, 1, 1, which have decimal equivalents of 0 to 7, base 10. But what I've done is I've shifted my negative sign to the lowest point here. So my negative 5 volts is going to map to 0, 0, 0, and my positive 5 volts is going to map to 1, 1, 1. And then my 0 volts maps to, 0 volts doesn't get a number in there. Oops. It's not a problem necessarily, but it is kind of a quirk here. So we do have code values between 0, 0, 0 and 1, 1, 1, which is 2 to the n minus 1. But I don't necessarily have a 0 voltage value. Now, you can fix that slightly by putting in your 0 voltage value and not using that upper plus 5. But the general idea is you're still going to use positive decimal equivalents, positive digital values, but negative voltages. So we could also do sign extension. Sign extension says that we're going to assume that the most significant bit is our sign bit. So we're always going to have a positive or negative sign on that most significant bit. So these digital values here, that first one is a positive or negative. So 0 corresponds to positive, and 1 corresponds to negative. What does that mean? Well, it means you're going to only have the remaining bits. In this case, we had 3 bits to start with. We only have the remaining 2 bits to actually quantize the number. So we end up with running our code values from negative 2 to the n minus 1 minus 1 up to 2 to the n minus 1 minus 1. So I can still map negative 5 volts to positive 5 volts, but in terms of decimal equivalents, that means I'm going from negative 3 to positive 3. Also notice that I've got 2 values of 0 showing. So I've got essentially a positive and a negative 0, which is sort of weird, but not the end of the world. Also, in terms of our counting scheme, notice that we start from 0 and we count up to plus 5. And we start from 1, 0, 0 and count up to 1, 1, 1 and negative 5. So the last one is 2's complement, and I would say this is probably the easiest one. Sorry, not easiest, best one. There we go. So in this case, we're going to start at 0, 0, 0 being 0 volt, and we're going to count up to our plus 5 or our plus 3.75 on the other one. And then we're going to wrap around and count up again. And in our decimal equivalent, notice that we go from 0 up to a positive 3 and 0 down to a negative 4. So we don't end up with 2 zeros anymore. Now we've got more negative numbers than we have positive numbers. And so same sort of thing, we're going to have a negative 2 to the n minus 1 up to 2 to the n minus 1 minus 1. We've got one more negative value than we do positive values. So why do we do this? Well, we do this because the math works. So if we've got numbers like this, same ones from the previous page, and we say, hey, what's negative 3 plus 3? Well, negative 3 plus 3, hopefully you look at that and you say, well, that's 0. So what does that mean in terms of decimal equivalents? Well, or digital equivalents. So I've got negative 3, here it is 1, 0, 1, and positive 3 is 0, 1, 1. So if I add those together, 1 plus 1 is going to be a 0 and carry the 1. And 1 plus 0 plus 1 is going to be a 0 and carry the 1. And 1 plus 1 plus 0 is going to be a 0 and carry the 1, except I only allocated 3 bits here, so throw that away. And I've got 0, 0, 0, which is 0 in decimal equivalent. So the math did work, our subtraction operation works, which is great. So 2's complement is really good in terms of doing math. Multiplication and division work as well, but I don't have examples for those. So sometimes you're going to end up in a case where you have different numbers of bits between your A to D and your D to A conversions. So if you are reading in a voltage and then writing that voltage back out, you may have different precision on those two. And so you can deal with that by always padding your numbers with zeros or ones appropriately in order to get back and forth. So this does happen on the Arduino, for instance. We've got a 10-bit ADC, but we've only got an 8-bit DAC. So when you go back and forth, you do have to account for the fact that they're different precision. So one last thing here, floating point numbers. We do use floating point numbers a fair amount. Floating point numbers, it's important to understand, are actually binary numbers when you deal with the stuff under the hood. Now, we're not going to deal with the stuff under the hood. We just want to recognize that they are, in fact, floating point numbers. So if you want to look up all the details, it's IEEE standard 754. So this says that we've got a -1 raised to the s times c times b raised to the q. This is how we represent a floating point number. So s is our sign. So it's either a 0 or 1 to say, is it going to be a negative number or a positive number? Not that different than what we were just talking about with our most significant bit being a sign bit. There is the c value, which is our coefficient, also called a mantissa or significant. We got a base, which is either going to be 2 or 10. And then we have an exponent. So for instance, pi is represented here as a positive number. So we have -1 raised to the 0. And then we've got our coefficient. And our coefficient could be in terms of base 10 coefficient, this 314156. Or it could be in terms of this long one that I'm not going to read out, which is our base 2 coefficient. So the base 10 coefficient is then the 314156 is multiplied by 10 to the -5. So our assumed base is 10, and then our exponent is -5. And so if we have a scheme where everybody knows that this is the scheme we're using with a base 10, then we only have to code the 0, the 314159, and the -5, and then everybody knows what number we're talking about. Same sort of thing with the base 2 version. We can code that long thing, and we can code the exponent and the sign. So looks something like this. We've got our 32-bit and 64-bit floating point numbers here, also known as singles and doubles. Doubles are the older ones, singles are the newer one. This is the base 2 version. So you can see that the base 2 version has a sign bit. It's got a chunk here associated with the exponent, and it's got a chunk here associated with the fraction, or the coefficient, as I called it. In the double version, it's just more bits for each one of these. But that's how we represent our floating point numbers as binary. Now, again, we don't need to worry about that too much because the processors that we're dealing with and the compilers are going to do the magic for us, but it is actually binary numbers. So at this point, I am going to, I got one more slide. I forgot about this one. So we also have machine epsilon is just this number that tells us how small a number we can represent. So 1 plus machine epsilon is greater than 1. So how small can we get machine epsilon? Tells us how much error we're going to have in a representation. So for instance, this is taken from MATLAB. And you can see that the machine epsilon, the smallest number here that we can distinguish, is on the order of 10 to the -16, which is pretty small. So we can represent pretty small numbers in MATLAB. And this depends on what type of data type you're using. All right, so I'm going to stop here, and we'll pick this one up with the next video.